The plan is that an author of a poster comes to the podium and gives an overview of the poster in the same way as if it would be the actual presentation. Note that here it is everything enlarged. Actual poster will be 3 by 4 feet maximum, so try to use bigger fonts. And the audience try to give hard time to the presenter, catching on the scientific inconsistencies or weakness in style of presentation. So it is not personal, it is for improving the quality. Also, the new group members who just joined and who never been on Assemble may see how it goes with senior group members and then just follow the same pattern. So those who will come next week may just get less fear by watching how it will happen this time. What else?
So, does Levi, can you hear us?
Yeah, I can hear you. Can you hear me?
Yeah, can you see the screen?
No, I can only see Dimitri.
Huh.
No, it's nothing interesting in seeing
It will be a
Dmitry.
star for today.
No, let me.
You can just share the content.
Yes, you're right. Do you see? What do you see now?
I think
I
now
see me and you.
Yeah.
No.
I think you need to refocus the camera, so the camera should look on the screen.
It says receive content.
Well, maybe they under content they imply your figure. Okay. How about this one? Just focusing the camera on the display, on the big screen.
It will work, but it's not optimal.
Well, if the poster is optimal, then everything is in big fonts and very visible. And you also have the copy of all materials in your email. At least you should.
When did you send that?
5 minutes ago, before departing from the office.
Oh, okay.
So we do have, I hope everyone got poster templates, just in case you're doing it for the first time. We all have place to stay in Senegal. Don't forget to make the travel authorization. If you haven't done, please do, and mention whoever promised you in private discussions to support your travel, this person. In your travel authorization, and then it should be approved by email, and then secretaries will be able to work on your reimbursement ahead of time. They need it to be done not in the last moment, and definitely before the travel starts. Those who you may have done it in the past. Here, I guess you. What else? Data flights. You know, also the airport is about 1 hour or even more drive from the conference hotel. So you may want to find a way to get there, which is renting a car, finding someone who will give you a drive, like sharing ride, or getting a shuttle. And if you plan to get if you want to be reimbursed by NDSU, they allow only 2 companies, the enterprise or Hertz, and there are corporate codes that make the rental expenses much less. And they add like everything will be covered in sense of insurance. Abstracts are not yet available, but they will be soon on the conference website. And here is the list of the presentations for today. So the black ones are for today, the red ones are for next week, and then probably we will reiterate once again. So if you do not like the quality on the screen, you can go on the link and see the works on your laptops, just as an opportunity. Probably you do not need it. And here are the printouts of for the first speaker with distributed. So the idea is that while speaker presents his or her poster, the audience tries to make notes on this copy. Make notes, tell what you do not like or what you like, and then after we complete the discussion, you submit it back to the author so that the author does see a feedback and can constructively improve whatever is on the poster. So with this, I would like to invite Dr. Yuan Han to I'm a little stupid in making it to the full screen, but maybe you can just scroll through and focus on different areas.
F11. That might help a little bit. Click F11. F11 on the keyboard. Helps a little bit.
Okay, so my topic is computational modeling of photopolymerization reactions of cyclohexylene, or CHS. So CHS has attracted much attention because it can be used as silicon sources to prepare silicon-containing materials through liquid-based methods. And CHS is also an alternative to monosilane in chemical vapor deposition techniques. So to the preparation of silicon-containing materials from CHS follow a general chemistry. So basically, at first, the CHS molecules undergoes brilliant opening polymerization due to thermal or photo treatment. And upon additional thermal treatment, the polymer will undergo some bond breaking events, such as the breaking of silicon-silicon bond and silicon-hydrogen bonds to form amorphous silicon. So the experimentalists have already characterized this feature through some techniques, but the corresponding theoretical investigation is missing. So that's the reason we are doing this kind of simulations. So here are my computational details. So basically, we are using time-dependent excited state molecular dynamics to capture this polymerization process. And here are my results. So basically, we have two models. The first one is two molecules in our face-to-face configuration. The other one is two molecules in our side-by-side configuration. And after running geometry optimization, we have this kind of basic electronic structures. And one of the interesting observations for these initial configurations, they have relatively large band gap. And here are the calculated absorption spectra. And we can see there is no absorption in the visible range. That means at this stage, it is transparent, which is consistent with experimental findings. And after that, we use these models as an input for TD-SMD calculations. And here are my results. So for example, for this trajectory, at this specific time, we can say two molecules are connecting with each other because of some bond breaking and bond formation. And here are the calculated density states. And we can say the band gap reduce from 5 electron volts to 2 electron volts. And at this time, these molecules do have absorption in the visible range. So this is another demonstration that we have the polymerized product. And finally, we can just get the simulated mass spectrum from TD-SMD trajectories. And so the most strong peak is corresponding to the single molecule. And so this range corresponding to products with mass higher than the single molecule. So that's an indication of polymerization. And here is the fragmentation. I guess that's it.
Okay, let's thank Dr. Han. So, yeah, please.
I just have a suggestion for your. It looks like you excite like your figure in a very right column, right? The top figure for results of mass spectra, right? So these different panels corresponds to the different excitation energy, right? Well, you're saying it's like HOMA -5 to LUMA +5, HOMA -2 LUMA +4, right?
I believe B and C correspond to different excitation energy.
Well,
A is from different configuration.
oh, this is unclear because in your, like I'm reading what you have, you say A, HOMA -5 to LUMA +5. Oh, I see. Okay, I would say no one really will be coming and reading the captures, right? Because it's a poster, it's not a paper. So I would suggest, first of all, you probably can use red arrows or whatever, the color for arrows corresponding to, let's say, your colors of this mass spectra, in your figure, in the middle column on the top of the spectra, right? Like, what is exactly your HOMA +5, LUMA to +5 transitions on the spectra? Is it the first peak or second peak in your spectra?
I guess like here.
No, I'm talking about absorption spectra,
Oh, I see.
which of course correlates with your ground state as well. Your panel C and F. Yeah, the central top figure, like if you're saying that your red mass spectra corresponds to the some optical excitation, right? With the configuration A, right?
Mm-hmm.
Or whatever. Face to face, I think it's your A.
I guess maybe something here.
Oh, really? So far away? Oh, it's nanometer. Sorry, I thought it's electron volts. Yeah.
So
Okay. Anyway, so my suggestion would be really show the arrow. Let's say red color on a top panel because it corresponds to this excitation, and then it would be easy for people. And then of course you need to explain, but it would be clear. Oh, if we take this excitation from this configuration, we see this mass spectra. Then you use your green arrow for the bottom panel, right? I mean the panel F, showing where its excitation's there, and then another blue also on the F panel, showing where how this excitation is different for the second case, right?
Mm-hmm.
So then it would be easy to correlate the results, like it's not just result 1, result 2, result 3.
Yes.
And I think it's visually would be easy to understand the difference without really reading, and for you probably it would be easy to explain, so you will not spend all this time if someone asks.
Yeah. Mm-hmm.
Hey, Yulun,
Mm-hmm.
why do you show your absorption in EV if your DOS is printed in electron volt? Because then you have to do the mental jumping back and forth to try and relate the DOS to the absorption, because I would assume that the peaks correspond to transitions between bands in your DOS, but it's relatively hard to go back and forth to figure out which peaks are which, comparing the absorption and DOS.
Yeah, I can make them consistent, but here I just want to emphasize at this moment there is no absorption in the visible range. So
Yes, and that's fine. The thing for me is, if you want to try and relate DOS to absorption, it's much easier if they're in the same units.
mm-hmm.
Yeah.
May I ask?
Yep.
Well, in one sentence, what would be the main achievement of the poster? What is uniqueness different from similar simulations?
I guess maybe there are two nowadays. The first one is we can actually capture the photo dimerization process. The second one is we use a relatively new method. And previously, this method was used to characterize the photo dissociation process. And this time we use to capture the photo polymerization. So it's kind of indicates the university.
So because it is a first principles molecular dynamics, it allows to describe bond formation. And specifically here, it shows formation of a bond between these monomers. So you may consider to highlight this main result maybe by an arrow from the group of figures in the center, top, to group of figures in the bottom. Like maybe make an arrow showing like from H bar omega by light, one goes from here to there. From this structure to this one, and then if a visitor of a poster comes for maybe 30 seconds, you can tell, here's the main result. Rest are technical details.
And again, returning back and connecting this figure which Dmitry was pointing and your mass spectra, like would be also interesting kind of to know, like for example, your G structure from your middle bottom panel, right? How's this, yeah, like this structure, where is it exactly in your mass spectra?
Something like here. Because this paper.
Or I would rephrase it. It looks like because you will have, like, am I right, that intensity of each of these peak in mass spectra telling you really which of these configurations after the polymerization, which of them are the most probable, or in the most amount, present in the most amount, right?
Yes, the intensity related to the
right.
probability.
And it looks like in a case if you excite in your A case, your this position, right, and you excite in at this energy, you have presence of all of them, but kind of really all species are present, right? There is maybe a little bit more for this C6 case, right? But when you excite, like when you have this other configuration and you excite, as I understand, that slightly different energy, then you have more kind of distinct more distinct structures. Like you have really only three main peaks, right?
Yes.
With again, largest for C6, much more pronounced C6, but also just two other configurations, SH4 and SI4 and silicon 12, right? And for blue case, again, you change in the excitation energy and you just slightly increase one of these species. So I would say, like, what would be, like, at these specific conditions, if you excite at this specific energy, then which configuration among these A, C, E, G structures on your middle side would be the most present, the most probable to obtain? Oh, you don't really show it in this figure. Without counting, I would say all your structures here have more than 6 silicons. But it looks like that in all cases, the majority coming from silicon 6, H12. And I understand that silicon 6 now is not a ring anymore. It's a line, right? It's a polymer now. It's not a cyclone.
Yes, but the problem is here. So right now I just show configuration at this specific time. But the mass spectra is an accumulation of different configurations.
So then again, it would be interesting to see, since they are present here, right? So is it formation of these structures at the initial moment of time, maybe in the first moment of whatever your range of time, maybe first 200 I don't know, femtosecond, picosecond, and so on, and then you have silicon 12 appearing later, or like again.
Yeah, I can do that. I can do the time-dependent mass spectrum. But right now,
Or maybe not really doing it. I don't think but you might have, like, again, maybe just discuss it in this context, right? Not just, oh, this is my results and this is just snapshots of this configuration. Again, I would really prefer when you really connect all your results together, making as one story, not like story 1, 2, 3, which have really no connection, right? So if you're saying that this is configurations which are appearing during the time, right? Then again, and like means that majority, or like you have a big amount of them appearing right in the mass spectra for silicon 12, whatever, some of them I guess is appearing really, right? And you can say, oh, and this happens really when you're waiting for this amount of time. And at the initial moment of time, for the first 200 or whatever units of the time, we will see only formation of the silicon 6, maybe. I don't know, like yeah. Without really making a big difference, but just because you will have a chance to explain and showing how all this connected, right? So I would suggest to really think about how you're really connecting this, and maybe, yeah, maybe graphically also you find a better way how you can connect them. But at least by words, really, because this gives you, like, exactly answering to my question, but you probably can introduce it to your explanation, and then people probably will get much better ideas what's going on.
Makes sense.
More questions to you?
I have questions on your conclusions. So your first one doesn't really give me any information that the introduction would give. It just says we run this new methodology and that's it, correct?
Yes.
Is that a conclusion, or is that something that would be in the introduction?
Or maybe methodology.
Yeah, I guess maybe it can move to methodology.
And then the second one is a similar case. You pretty much just say, we do this in our methodology, without saying, without this, it would break down. Yes or no?
Could you please repeat your question?
So the second one says, to minimize the bond breaking and bond elongation events and blah, 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 we do a post procedure technique to apply whatever. The only place I saw that you did that was in your diagram between your TDES, whatever your method's called, and then you do post-processing. Did you say any other things other than that diagram for this point?
Not really.
But is it really important issue here? Like, you're saying that, like, this is really based on a development, or how to say, improvement of the methodology, right, this part. And this is like your observation, that if you just run it without this specific step, you're getting some unphysical results, right?
Right.
So, and that's why you have to, like, you really, like, this is probably a good way for the conclusion, but maybe you need again to say it very clearly that when you explain methodology, right, so that one thing which you are doing is advancing, extending, doing something, right, developing better, or wherever your work would be here. Like, you're applying this specific procedure, which extending the overall regular procedure which was already developed, right? You have to do it because otherwise your results will be not physical or something, right? And maybe, does it have really some physical meaning rather than just technical issue? Like this post-processing thing. Is it implied?
Let's ask Wasser.
Oh, like this thing to mimic exactly the experimental setups, or this is what is just technically has to be involved to the structure, to your methodology processes?
I guess in this case, it's just from technology point of view to minimize uncertainty of the structure.
But then why don't you have any other data on that on the poster? If that's a critical point, why isn't it somewhere on the poster?
What is the proof that you really need this step? Do you have a proof for this?
The proof maybe for example, if the post-processing is not applied, then the structure of this configuration will be very strange.
But
What do you
there's no
mean
proof
straight?
for us to
Line
see.
or
That's
what?
only taking your word.
Can I add additional question
Yes.
which will make discussion more constructive? In experimental setup, we may imagine a chamber where reactant is irradiated by light, and we may imagine a chamber where the products are analyzed by mass spec. What happens to products while they are traveling from reaction chamber to characterization chamber?
I see your point. So you are saying there is a relaxation process.
Yes. Right now, it is not our goal, but in any setup, relaxation happens. And it happens on much shorter time than it takes for any molecule to travel on a substantial length.
Yeah, this is kind of almost similar questions actually. From the mass spec, I would just assume that if I look on the mass spec, the highest interspec in the is the Si6H12 in 3 cases. I mean, all of these cases.
Yes.
And the second highest is like Si12H24, almost in the all of these cases. That means the two separately two different ring that have no bond anything. Because Si4C12H24 means, right?
Yeah, let me explain the process. So basically, we start with these two configurations. So each of them is silicon 6, and as time goes by, the system accumulates kinetic energy. So first, these two molecules just approach to each other, and they have some ring opening polymerization. So they connect with each other. Then, because of this ring opening polymerization, we see this silicon 12 hydrogen 24. And with time goes by, because the cumulative energy is high enough, then we can see the hydrogen desorption, so that we can have this kind of small, relatively small peaks, and then we can see the fragmentation of this polymer, so that we have this species, this species, this species, this species.
Okay, that's one perspective. Another thing is, if I look on here, significant amount is a very smaller fragment after this all trajectory, right? It's formed a fragment, very smaller fragment like Si2, Si3, those kind of things. So that means if we relax down, it can form like any compound, like they can bond
Any
together and
polymer.
any kind of polymer. I wouldn't say exact polymer, could form different size molecule in that case. So what is the reason of saying is polymerization or dimerization actually?
Yeah, from this perspective, maybe dimerization is more accurate, because we only have two molecules in the system, right?
Yeah, but is it forming like bond breaking and bond forming and forming new molecule or a polymer? Because we know that polymer is just ordered bonding of monomer and forming a specific
For polymer, you
orientation.
should have unlimited number of monomers, right?
Yeah, monomers. But now it's just bond break and they form bond and give you the different molecules.
Yes.
So is it kind of more controlled polymerization or just a...
So let me translate the question of Jeff.
I'm just wondering, yeah.
Why in this upper central figure you have only 2 monomers? Why not 3, 4, or 10 to satisfy Jabet's question?
No,
We have limited
maybe not that way.
computational resources.
No, maybe it's like, if I say like the 2 molecules and after the excitations, it's form a larger molecules or smaller molecules. And if I say the 2 monomers and form a dimer, you know the two states, difference of the two statement. like two molecules bond breaks and form different molecules, bigger, larger molecules or smaller molecules, or two monomers and form a dimer.
But let me help and answer. And it's fine, we have time because we have just 4 more things to complete
That's
today.
good for us.
So, what is the goal of this work? Which experimental process is model? It is formation of solid out of liquid precursor. Solid, infinite solid. Amorphous or crystalline silicon. Even if this method is perfect, what is your expectation? Or maybe it could be shown in a poster. How long does it take for a single cycle of this reaction? How much would it change if one take a reasonable amount of precursor molecules? Do you have a guess? It will grow exponentially. It will be very expensive.
Very expensive.
So this is demonstration of the critical reaction step for the minimalistic model. Then first we use computer for minimalistic model, then we use our head to project it to bigger systems.
But may I also add, like, maybe something to add as a goal or as initial introduction to this whole thing. So it's not just getting the liquid precursors for getting the solids, again, because the idea is that it's easy to use technologically and it's cheaper. In addition to this, they're also claiming that another very important feature that you, with this approach, you're getting less defects when you create a solid. And this is assigned to the fact that you really should have a polymerization, that you're not working with silicon 4, like not short units, which then kind of connected together when you're changing the temperature, pressure, whatever. Oh, and then they crystallize, right? Because this way, like regular way, you need like you have just a few crystalline, how they call it, sources, right? And then it starts decreasing temperature to the needed temperature for the crystallization, and then it starts growing a crystal, right? But you might create this way a lot of defects. So using these precursors, which are lone polymers, results on a formation of less defects, because you can kind of imagine that you're making a wall from large bricks comparing to small bricks, right? And if you're not a very good expert, using large probably will decrease, like make your wall to be more straight rather than having a small bricks. You will have doing all possible things, right? So it's actually twofold problem. I would say solution of the problem here. One is solid to get solids from a liquid precursors, right? Kind of avoiding gas phase and so on, which allowed. Again, because of this polymerization. And second, if you have really nice and long polymers, or I would call it not polymers, maybe oligomers, right? But they have to be more or less identical size. They should be long and let's say all silicon 6 or all silicon 12, or majority of them will be this length. Then when it's becoming crystallizing, you have a better chance to have less defects.
Yeah, but
and that's why I think his results are important from this point of view, showing that you really create majority of the species will be either silicon 6 or maybe silicon 12. At least this is my interpretation of his result, right? And of course it depends where you excite and the other properties which you can tune when you do this reaction. But looks like you might have really major contribution of one size oligomers. But they also create the dimers as well, right? So you have both. You create oligomers, so you kind of have polymerization, and you have also dimerization, where two molecules just connect to each other and stay as a dimer, right? Which may be not the thing which we want to happen, but it happens.
Yeah, I'm just wondering because it's formed like Si1 and Si2 is a very small fragment, so those peaks are very significantly higher and very smaller one.
In a top, right?
In a top,
that's right. It depends on the conditions, right?
In a last one, bottom one. So it may create more, what's it called? I mean, disorder, right? In this case.
Yeah, you do, of course. But again, looks like it's controllable, right? It depends on the conditions where you excite, and what exactly the initial whatever structure is. You might kind of have either top or bottom.
Okay. Last chance for questions to Ilun. If no, let's thank him once again. Yes. So I invite everyone to submit the feedback to the author. If any. And right now, Aaron Fordy is invited to give overview of his poster. You probably will be more efficient than I in switching the windows. No, it's okay. Or exit full screen.
Oh, here, F11. Okay.
This one should be yours.
F12?
Probably.
F11 again. This side goes back and forth.
Okay. I will slowly work. So please distribute. Tell me anything you like.
Okay, so I guess the project that I've been working on for the last couple of months is focusing on improving the photoluminescence quantum yield of perovskite quantum dots through doping with transition metals. In this case, we're using manganese ion. And so I guess in general, fully organic cesium lead iodide perovskite quantum dots are pretty popular for light emitting technologies because they're good absorbers and they're very good emitters. So, and they're very easy to synthesize. You can use regular colloidal synthesis or wet solution synthesis to make them, which is attractive for making materials like this. But the conflict arises due to the ligands of the quantum dots. The ligands that are used to synthesize them have been shown to not be very strongly bound to the surface, and they kind of fall off over time. So as those ligands fall off, they create trap states on the surface, which decreases the photoluminescence properties over time. So basically they degrade, basically. And then to resolve this conflict, some people have looked into the doping these quantum dots with manganese ions, and this has been a technique that's been used, I don't know, basically for the entire history of quantum dot synthesis to try to improve photoluminescence out of them. So basically it's people using an old method on a new material. And so this poster was originally for KU NDSU, and some of it I'm going to be deleting to make room for some of the new data that we've been collecting. But at that conference, one of the first questions we were looking at is what's the ground state electronic structure of the intrinsic quantum dot and then of the doped quantum dot itself, because the doped quantum dot the manganese ion can take on many different spin configurations due to ligand field crystal field theory. So yeah, in that crystal field, it can either take usually a high spin configuration like this, where there's not a lot of energy splitting between the states, so the spins kind of will take a high configuration, or if there's strong enough splitting to split the energy levels, it'll take a low spin configuration in the doublet. And what we found, that for perovskite quantum dots, you always take the high spin configuration because the halide ions are weak. I don't know what the word is. They're weak point charges, so they don't. They're not very strong splitters. So anytime you use halides, it's usually a high split or a high spin configuration that the manganese ion takes. So the implications of that is, if you're in a high spin configuration, to get an optical transition between the manganese quantum dots, you have to have a spin flip occurring, which is usually forbidden under absorption or selection rules. But in this case, the manganese ion has a small amount of spin orbit coupling, so there's a small probability of a spin flip transition occurring due to mixing the spin states. So what we did is we looked at ground state configuration and are people still following? I just feel like I'm kind of rambling.
No, you'll hear questions soon.
Okay, so I guess to fully investigate the possible optical transitions in these systems, we looked at spin polarized calculations. So here, this would just be the red is your alpha electrons, and then your bottom are your beta electrons. And we also looked at density states for the spin orbit coupling enabled calculations, which is this guy. And what we did is we plotted the orbitals for the spin polarized calculations. And what we found is like this is, you can kind of imagine as like your band edges of the quantum dot, and then on the inside of the band edges are the manganese states that are optically active. So here would be, so the three possible transitions that we can have from the manganese ion would be metal to ligand transition. So we have transition from the metal to a ligand, or we can have the metal spin flip transition. So from here to any one of these guys. And we can also have a ligand to metal. So it's, you can't see it, but it's the orbital's on a ligand here, and it can transfer to the manganese states there. And you also have the possibilities, I didn't draw them in, but just the intrinsic transitions between the quantum dot as well.
Aaron?
Yep.
Can I interrupt in the middle?
Mm-hmm.
So, if you have very short time visitors of your poster, how you can explain or convince that there are ligands and metal, and how do you see that orbitals are localized on specific type of ions? Do you have labels, or you will make it very visually appealing? Because you are telling metal to ligand, but from here, even at this zooming in size, it all looks like distributed clouds.
Mm-hmm. I guess.
How are you going to address it?
Well, I do have a model of the quantum dot up in the top left, but even that's kind of hard to resolve. Because like in the middle, you can kind of see it if you're looking, there's a green dot, which is the dopant. And then there's a bromide ligand field around it, which I illustrated here. But I guess I do have an image somewhere where it's like an atomistic model of just the dopant and the surrounding ligands.
So you can zoom in of the vicinity of manganese ion.
Right.
So where you see only manganese and very few surrounding ions, and then one visually can identify where the charge density is.
Mm-hmm.
Right? I'm just guessing that you plan to do so.
Yeah, I planned on putting that one image. I don't know. I think I sent you in a PowerPoint one time, putting that image in here, and then also, just rearranging it to be more explicit. But
I want to add a comment with this one. You already printed with the axis too, so it seems like you change the orientation of the molecules. So if you put the all orientation in the similar orientation of all image, it would be help to understand like where the orbital is located in which side. Because from the axis, I just look on there is like different orientation. I mean, all is not from the same view.
right, but I don't know if you can see it on your screen, but there are like coordinate axes.
Okay.
So you can kind of, I don't know, imagine or use some imagination to tell how they look relative to one another. And the way I did that is because that's just the way the orbitals look the best. That's why I changed the orientation. Because it's kind of hard to tell that this is your x squared orbital from looking at it this way or looking down the line. So I just oriented it so the orbitals look prettier.
Yeah.
So then, yeah, and then from the orbital pictures, we can kind of characterize some of the optical transitions from the electronic ground state. So this orbital, you can't see the little humps, but there's little regions of density in between the gaps. So those are from the manganese ions. So that would be a metal ligand charge transfer, and this would be ligand to metal charge transfer for the spin polarized calculations. And then for the doped quantum dot, we also still see that we have our doped quantum dot with intrinsic spin orbit coupling. So we still see that we have some of the manganese states still inside the gap, but then the optical transition, the spin orbit coupling has the higher manganese states lower here. So that would be a metal-metal transition. And then
Metal-metal transition, but not metal-to-metal charge transfer. What do you have abbreviation MMCT?
mm-hmm.
Does it means that charge density goes from one metal to another metal? Or is just excitation on the same center?
Or yeah, it goes to itself, so it's
So
yeah,
just
same excitation.
Just MM.
Something like metal-metal. Okay. And I guess, and then since we're eventually going to be doing photoluminescence of these perovskite quantum dots along a molecular trajectory, we looked at the oscillator strings for the ground state configurations for each of our systems. So we did it for spin polarized, which are black and red. Blue is just the intrinsic quantum dot with regular ground state calculations, and then the pink line is the intrinsic quantum dot with spin orbit coupling. And it's kind of jumbled here, but one interesting thing that was found from looking at the oscillator strings, comparing the spin orbit or the intrinsic quantum dot with the intrinsic quantum dot without spin orbit coupling, and the dot with spin orbit coupling, is we see at least a 4-fold enhancement in the excitement or the excitation intensity, which is, I don't know, it's not expected. It's kind of an interesting phenomenon that spin orbit coupling mixes the homo-lumo states together, so you get a brighter transition. And that hasn't been observed in the literature before, and it's if nothing else, it's a good indication that for if you're going to be looking at optical transitions in these systems, that you need spin orbit coupling to accurately describe them. And then I guess once enough data is collected for couplings, I'll have some excited state dynamics on here too that I'll have to fit in. I guess, yeah, I'm ready to take questions.
Okay, let's thank Aaron.
So again, looking at your conclusions, maybe just can you highlight once again what is your main results, main outcomes of this work? 1, 2, 3, not
So-
more than 3.
So the ground state configuration for the doped perovskite quantum dot takes a high spin configuration. So that means that we have to use spin orbit coupling to describe optical transitions in these systems, because the only way it occurs is a spin flip. So we can't use spin orbit for those, or I mean, spin polarized calculations. So that kind of forces our hands right away into how we're going to compute these. And then
But here is, like, if this is your main conclusion, right, I'm a little bit confused, like, look in your green box, right, you're saying that this is assumption, right, hypothesis.
mm-hmm.
So, like, you don't know which of this configuration is the most available, right?
Right.
And then the proof that you're saying that it is in a sextant rather than in a doublet configuration, in a high spin rather than low spin configuration. Just because this energy of this state is low, then down, right? This is the only proof. Like you start with, we have this and this, but because the energy of sextant is low.
Yeah, and Oh, this is kind of cheating, but we know that there are DD optical transitions experimentally. So that's kind of a hint.
The only thing which I want to say, like how much they're really different. Well, you have these values, but I really have a problem to subtract these huge numbers. I'm just afraid it's like 5,353.23 electron volts. And then I have to subtract 5,355.66 and everything in my mind. So how big is the split in between these two levels?
It's about 2 eV.
It's more than
So it's really so big.
almost 2.4.
Because there was a lot of work, not on these materials, but just on regular metal organic complexes with iron, where you have unpaired spins, right, and multiple configurations are available. So there was a lot of work showing that the splitting between, let's say, quartet, like for iron type, like iron bipyridine, this kind of type of complexes. So the splitting, which of this, I think it's like triplet versus pentet configuration, depends on a methodology, DFT methodology, density functional. And you might have either this or this being the lowest one. But of course, the splitting between this triplet, pentate, and so on states was not 2 electron volts. There was much smaller difference, which allows changing a functional kind of switch disorder. So that and just some technical issue, like if you just based on your and you have regular, what functional do you use? Probably somewhere here I just didn't notice.
GGA.
Yeah, so you use this GGA kind of very simple functional for this calculation. So again, this alignment might be the effect of the functional rather than real results that your high spin configuration is the lowest energy configuration.
Yeah,
Just to be aware about this technical. I mean, I don't say it's incorrect, especially taking into account such a huge difference in these electronic states.
That's true. And then also, I think.
But just aware of these issues, there might be some questions on this.
Yeah. I think those are spin polarized calculations.
Guys,
I noticed.
I have to go. I have a meeting at 4. So, nice talking. I'll see you guys next week.
Yeah, thanks for joining, and please prepare your version next week.
Okay, sounds good.
What was I saying?
He's on travel.
Spin polarized. So I noticed that for the spin orbit couplings, it's like it dropped the ground state energy by at least like 6 or 7 eV between the models. So that might be something to check too between the doublet and sextet. How spin orbit affects the ground state energy.
Did you plan to check if the same conclusion reappears with different functional, like HSC?
I did not.
But
Yeah,
did you plan to do it in the future?
I can plan to do it.
Okay, that's good.
Might be important. Well, again. So so this is your and the second. This was your first main result. The second main result.
It's TBD, or it's the excited state dynamics, because the whole point of this is to show that.
But you don't show dynamics, right? Do you?
Yeah, they're still computing,
So then it's gonna be your main result.
or it will be my main result.
It will be. I'm talking about what exactly you got so far. This is your future plans to get great results, but not right now, right?
Right.
But I think it's in your conclusions, and I think that it's also on your figure for this lowest energy transitions, right? DD transition?
Yeah, the metal transition. So basically all this work was just to show what are the possible transitions that can happen in the dope system, and then what methods we need to use to be able to compute those transitions accurately.
But am I right that one of your main results that you can see this metal-metal low energy transition optically active, right? Only when you have a spin orbit coupling. If you don't, then you are not able to reproduce this peak, right?
Yes, because in spin polarized, spin's a good quantum number, so you can't get this one to flip up this way.
But how you? But has it to be there? Like there experimental evidence that they see this DD transition. So is it expected? Like
Yeah,
how you
there's
know which one is correct?
Yeah, it's experimental. They get like 600 nanometer emission.
So there should be low energy transition coming just from this impurity.
And it's kind of hard to see here, but there is oscillator strength for those DD transitions. I did point that out when I was looking at that originally. But, so they're there. They're not very strong, but
Okay.
over
So
time they might build up.
you kind of have it in your conclusions, right? But I would say it's completely unclear based on the structure of your poster what is exactly your main results, right? Because you have such a big amount of space used for this characterization of the orbitals, metal to metal, ligand to metal, which again looks like probably not very, like it's some technical intermediate results rather than your main results. And such a small little figure, which looks like, my understanding is that this is oscillator strengths over absorption spectra, which you're showing is probably one of the main, like actually your main result, right, overall. And probably this other figure on the ground state where you're showing the splitting between this doublet and sextant, right? So I would probably suggest to think about that. Maybe you can find a better way to use a space so you really can highlight your main results. Or maybe just putting frames might help if you don't want to really screw up the whole thing, right? So it would be clear where your technical things are kind of not very important, you just go in with analysis of your results, and where you have really the main outcomes for very valuable things which you think will be useful or needed for wherever, for your future work, for the work which is already known for experiment and so on.
I have a question in the same.
Because the spectra, the effect of the spin
relation.
orbit coupling, right, on the spectra looks like it's really very interesting and very important result. So
But
you
it's
should
just
not
as
really
pretty.
hide it somewhere with a very little figure there.
Yeah.
So, in the continuation of this question, you can maybe verbally address which results are expected to be included into the next release of this poster, and where will you put boxes to fit them? Because right now it takes the whole space. What are you going to squeeze, and where to, which new material and where to place it?
I don't know. I've been kind of visualizing in my head because, well, the first thing I have to do is I have it as a square, so I can get more space by making it rectangular long ways. So just increasing the poster size itself will give me some more room. I was thinking about maybe having this maybe a third, maybe a quarter of the poster. So shrink it down, maybe put it, I don't know exactly where I
Yeah,
put it.
and also like you have a lot of white space on your right side, right?
Yeah.
And again, it looks like your figures on the bottom, right, with your doors where you show in MLCT, LMCT, MMCT, right? These kind of figures. They're probably more related to these configurations because they're really related. So probably you can rearrange these guys and probably put these figures into your white space. So kind of just explaining that this transition corresponds to these orbitals. So that's why you call them MLCT and so on, right? And then you will have a little bit space on the bottom panel, which again, maybe you can say for your new results, or maybe just increase the size of this figure and maybe somehow highlight your main result as well.
Yeah, I mean, I'm going to take this out, then move this up, so I'll give some space here. Shrink this down, widen the poster out.
Oh, so you make it maybe 30% wider, and then you have the third column,
Right, so,
and put there about 30% of content with new results.
right.
Which you so
What are the new results?
yes. What are the new results? What do you plan to have?
What do I plan to have?
Yes.
You already announced that you will have new results.
And we have no doubt that you will. But can you open the intrigue and just sketch?
Well, I guess I don't have the pictures here, but if you're familiar with the fluctuation charts over dynamic trajectories, so it's the change in orbital energies.
Okay.
So along that trajectory for just the bare quantum dot, it shows characteristics you'd expect for surface states, so energy within the band gap. So that kind of gives an indication that ligands are kind of popping off the surface, coming back on during the trajectory. So
So you're kind of really having this trap states due to the ligand when they disattached?
that's what I'm assuming. I'm going to go through, figure out exactly which frame it is, and then look at that post car and then average the bond distances. And I think Yulin has a pretty good.
Since it looks like your spin orbit is important for the optical characterization, for the characterization of the optical features, right? I assume, are you involving spin orbit coupling into your dynamics or not? Or you're doing it without spin orbit? Yeah.
Not the molecular dynamics. So we do the molecular dynamics, take all the position files from that, and use that for our couplings. So during the coupling stage, spin orbit is used.
Ah, okay. But
So, so it shows up.
those disattachment of ligands, it just dynamics without spin orbit. But when you will be recalculating the couplings and electronic levels, how they're changing with time, right? Then at this stage you will include the spin orbit, which is not done yet, right?
Yes, they'll be, yeah, they're a part of the couplings into that information. So then, yeah, we expect to see, I guess I don't know, it depends on how long the simulation is, because it's basically weighting these small probability transitions over a long time to outweigh the high probability transitions that occur, or that can be sporadic. So it's, I'm not really sure what to expect, but one of them is going to win. I just don't know which one.
Okay, so fluctuations, which other new results you plan to have?
Well, are pretty excited state relaxation figures.
Okay.
And then the PL quantum
green
units.
figures.
Mm-hmm.
Okay. With and without manganese.
Mm-hmm. Yep, for both models.
And you probably are going to show some autocorrelation functions and Redfield tensors eventually, or you don't think there will be space for them?
Maybe in a top corner.
Okay.
So or maybe somewhere next to the methods, if I can condense that down.
So in your third column, you have three subsections: fluctuations, autocorrelations, and green relaxation.
Tentatively.
By some reason, so Jabot has blue relaxation.
Ah,
I don't know when you have green relaxation.
someone will probably have red relaxation at some point. Okay.
More questions to Aaron?
You use only one size of the system, right? Just one size?
One size of quantum dot?
Yes.
Yeah, so it's a 2 by 2 by 2 quantum dot for both of them.
Two of what?
Or
2 by 2 in which units?
Cells?
And what is the size of the cell? Roughly.
7 angstroms.
So what's the size? What's the size
Pretty
of your,
small.
huh?
1.5
Pretty
centimeter.
Tell the size of your model and
One
number of
nanometer,
atoms.
it's 15.
No, well, for GFT,
Oh, 7, okay.
it's almost
Yeah,
2 by
it's
2.
about
like
1,000
it's
atoms.
almost
How
2
many
millimeters
atoms?
size.
1,000 about?
1,000 atoms?
Yeah,
And
just a
7
little less.
angstrom?
Or no, so it's,
No, 1,000 atoms.
so
total.
one cell is 7 angstroms. So two cells, it would be the nanometer.
1.5 nanometer.
Yeah, 1.5
1 and a half.
nanometers.
15 angstrom.
And it is without
And it's
ligands.
3-dimensional, right?
And it's
Yeah, without
to
ligands.
this
Then
way,
lig-
to this way,
How,
to this
how,
way.
It's
so
nice here.
how large are your ligands on your top left?
That vary. They're like 3 bond links, 3 carbon bond links about.
Okay, and how much vacuum?
How many ligands, by the way? How many ligands do you have on
How
the
many
surface?
ligands? 54,
Wow.
48.
And
So
they
like
are
100.
amine? Amine?
Yeah, one's an amine and then one's a carboxylic acid.
Also, you have 2 different types of
Mhm. Yeah, 2 different charges to match with the surface.
Yeah, maybe it would be useful some way in methodology to give a little bit more insights into the structure of your quantum dot, right?
Mm-hmm.
Because some people might be not really familiar with perovskites, and they would be very interested, right?
Maybe Dimitri will make another toy model
Well,
that we can bring.
yes and no, because I'm not sure that you can really cover, like, show, like, again, it's like another interesting thing why you have 2 different types of ligands there. And is it really carboxylic or carboxylated? You have protonated or deprotonated ligands.
Deprotonated. It's 2 free oxygens.
So means it's negatively charged.
Yes.
Then, but your system is also negatively charged? With 54 minus
one-
charge?
No, one's 2 plus, one's 2 minus.
So you kind of balancing the charge due to the surfaces.
Yeah, because the exposed lead, because it's all ionic bonding, all mixed ionic, covalent.
Would you have another poster with this information somewhere? Well,
Can you scroll and show the
some
top of the
some
poster?
information on the structure would be very useful.
So, which types of ligands do you have? You showed here.
Carboxylic
Carboxylic
acid and then an amine ligand.
So, what's the charge of the amino ligand?
1+.
So, then how many amino ligands and how many the carboxylic ligands do you have?
54 carboxylic and then 48 amine.
So the charge imbalance is like 6.
Mm-hmm.
It's not so drastic. It's not like 50 charges that would explode everything.
Right.
It's roughly the same number of cationic and anionic ligands.
Mhm.
So it's a balance in each other. So it's neutral structure.
Well, not each. So they're satisfying the surface because the lead has a positive charge, and then the surface bromines have a negative charge.
But lead is 2+.
Oh yeah, did I say positive?
Well, 2+ and
2+.
bromine is -1.
Right.
So I don't know, and you have two.
Well, then they'll be
bromines.
bonded to other ones too, so the charges will. I don't know. There's some ambiguity there, but basically the amines bind to bromine, carboxylic, to what? On the surface.
And again, this structure is like how you create the structure. Is it well known? Has it been already studied experimentally, theoretically? Is it really proved, or you just guessing that this is a structure on a surface? Like, I mean, especially surface ligands, right? I'm talking about surface ligands.
How do you know that the structure is optimal? So that removing or adding more or less ligands will not make it more stable.
And why carboxylates? This is like, why not sials? I don't know. Why is this choice of ligands?
Because when you synthesize them, like originally you use oleoamine and oleic acid. So these are basically just the functional groups of oleic acid and oleoamine. So they correspond to what experimentally used to synthesize them originally.
So there is experimental proofs
Mm-hmm.
that at least this is a species which have to be on the surface, and how much of this or that you kind of guessing based on the balance in charge, on the overall surface effects and so on, right? Like
Yeah.
knowing your surfaces.
Yeah. And then if you look at them under a TEM, they literally make like little squares that pack together. So they are definitely symmetric.
And you have citation for this.
The top of the, just after that.
Oh, this unreadable small font is a citation for experimental evidence.
Yeah, that's for the DD optical transitions. Yeah, I kind of ran out of space for.
And another problem, you are out of acknowledgement and you don't have space for acknowledgement. This has to be squeezed somehow. You need to find the space for acknowledgement.
I can put it in the green.
Whatever the color does matter. It can be green acknowledgements, yes.
You
what
have
is
green
the
dynamics
size
and
you
green
said?
acknowledgement.
What is the cell size you said again, please?
Cell size?
Font size?
No, I mean the
One unit cell or the whole quantum dot?
whole quantum dot.
No, it's like 1.5 angstrom
I'm just wondering how
1.5
it's called.
nanometer.
or nanometer. Yeah.
50 nanometers.
So 1 unit
How
cell.
1,000 more than 1,000 atom is placed in 1 nanometer. That's
It's together with ligands, right? So the size 1.5 is without ligands.
Yeah, most of the atoms are ligands in the system.
And then if you
Oh,
and then
okay.
54 pretty bulky ligands, so of course it's
So you may just add the chemical
No,
composition
I
like
got it,
equation.
yeah.
How many cesium, how many bromines.
So what is your calculation cell size? I mean, your periodic cell size.
I think it's like 31 by 31 by 31.
Okay, now that's
So it's
makes
like it's
sense.
7 angstroms of vacuum.
Okay, I got it. First I thought there is 15 angstrom, and I guess how is possible to put this much atom?
No, it's the actual size of the
Yeah.
structure which is shown. And again, you can say like it's very easy to add this diameter size, right? I don't know. Maybe even make a box to show the size of your crystal of your computational cell, right?
Mhm.
With the sizes X, Y, Z. And then you probably don't need to spend a lot of time for explaining it, and people will get it pretty quickly just looking at this figure.
More questions to Aaron? If no, let's thank him once again. So please join me in submitting the feedback to the author. Your place is here.
Yeah.
I'm
Okay.
collecting all those. I will give the letter on here.
Yep.
Well, and I have another thing, just to add. It looks like excited state dissipative dynamics is not really done yet, right?
Right.
But you're taking space for showing these formulas. Why? Like, it's your future work, but you probably don't need to go into the details with this future work.
Or you are so confident that next week or in 2 weeks you will have the results.
Hopefully.
Okay.
Uh,
So you think that these results will be on this poster
Oh,
anyway?
for Sanibel, yeah.
Oh, okay.
Like, yeah, we should have at least 50 couplings, which is roughly what we need to get a good average. So, yeah, it'll be on the Sanibel poster.
Can you help to? Oh, you did.
Yeah.
Thank you so much. Now the next speaker is Abu Muhammad Jabir. And
Should we speed up a little bit, right?
yeah. And previous speakers have chance to revenge for tough questions Javed asked to them. If you did.
Can I
Yeah.
have one, please? Yeah.
Oh, you do not know what you are going to present?
No, I just want to take note and just. So thank you everyone, and another thing is a pretty old poster actually, and I will include the more significant new information here. And so I'm working on the 2D nanoplates of lead selenides and lead chloride bridged lead selenide nanoplates. We know that the lead selenide quantum dots is getting attention for its application in solar cell applications because of promising feature of the multi-photon exciton generations and other things. But applying the quantum dots in the real field and the real solar cell devices sometimes is very difficult. So, and we assume there is people thinking that if it can possible to create the 2D nanoplates, that would be enhance these properties somehow. And so that's why, and also they have one Dr. Klimov groups from the Lano, they are able to synthesize the 2D nanoplates at the control thickness with the lead chloride, lead halide bridge, because they are able to synthesize the lead chloride and lead bromide bridge and lead selenide nanoplates. But we don't know the detailed excited state properties and how relaxation rates, how it's possible to multi-exciton generations perspectives. So that's why we just trying to study these excited state properties to figure out some feature which could help for multi-exciton generations and related properties. So this is one of our, in this section I'm just using the methodology, I'm not going to in details here. So in this one is just explaining my system, a study system. In the experimental one, they just took this small unit cell or lead chloride. They have in 110 facet, they put the lead PbCl2 lead chloride atoms, and then that's a precursor. And with the time, they saw that it's formed 2 nanometer thick, around 2 nanometer thickness, and 2D nanoplates like this one. Like if I put the 4 unit cell, we will get this kind of 2D nanoplates. I'm just showing one visualization here. And now in the first study, we took a look on there and DOS, how the DOS differ and when with also fragmented DOS. Also, this is same color. I will give you the different color in the final one. In the first one is showing the total loss. If you look on the total loss, this is the density of the total loss with the time. This Zx is the time. I took with the molecular dynamics trajectory, I took this DOS of the at each time step. And at the all times is like intensity of the balance band and conduction band is almost the same, so it's very comparative and similar density. But on the fragmented dose, I look on this and like this for the lead, and lead is like conduction sorry, conduction band is a little bit higher, and in case of cadmium is contributing in the conduction band is in the higher intensity, but in the bridging element, lead halide elements, if you look in here, it significantly contribute only in the balance band, not that significantly on the not that much in the conduction, but it still is have a. Another thing is chlorine is not contributing in the band age state. It's very hard to, it's not very distinguishable here, but it's contributing only in the deep inside the conduction bands and the balance band. So we thought that although these nanoplates are bonded with bridged through the lead chloride, but maybe lead chloride doesn't interfere with this excitation or relaxation process until it's exciting to the high energy. In the next, in this one, I just we use the fused surface hopping methodology to look on the relaxation rate. And this relaxation rate, I plotted the two initial conditions. First one, I took the asymmetric excitation, considered the symmetric excitations. And another one, next one is symmetric excitation, but their relaxation pathway is very significantly different. If we look on the first one, the symmetric one, is initially is electron exciting from the deep, hot hole is creating the hot hole here, but instantly is just relaxed down to the close to the HOMO level. So, but in case of if excited to the band close to the LUMO one, so it doesn't the relaxation pathway is on mainly depends on the hot hole. And in the symmetric cases, since these are primary condition, initial condition of symmetric, so it's creating the symmetric energy of hot hole and hot electrons, and its relaxation rate is almost similar in the both cases in the symmetric in the. And this is another presentation, the similar presentation of this result with the energy dissipation rate with the time, and this hot hole and electrons, and with the exciton. And it's almost showing that it's, forget the exact value is over here. It's going to be almost less than nanosecond, less than picosecond relaxation rate is relaxing to the HOMO level, and lowest excited state and lowest unoccupied state, but in less than picosecond one. And this is pretty much all the information here. I will include actually now is need to be compared with the quantum dots, because you already know that lead solenoid quantum dots are promising for these applications. So I'm going to simulate the relaxation pathway, relaxation rate, and with the quantum dots, I'm almost there, so I included this information. Then we can compare how lead halide bridging differ the relaxation rates. It's important here. And another thing is I'm also trying to calculate the dephasing rate, how fast and or slower dephasing rate. Then we can compare this result. Another thing is this all of those calculations have been done on the gamma points. But when I calculate, we know that the bulk lead solenoid band gap at the L point, and when I calculate the dispersion curve also for the 2D nanoparticles, it's also showing that the gamma point band gap is not actually lowest band gap, is a direct band gap is showing on the L point. So it is also important to find out the excitation pathway on the band gaps of the L point. So, and I think maybe it won't be possible before doing that, but I will discuss about this dispersion curves on my poster too. And this one is I'm showing the experimental result here, and my calculated one. This experimental is my calculated one. absorption spectra is pretty much blue shifted in compared to the experimental one. Experimental one is close to the, is showing that lowest band energy is close to 1200 nanometer. That means it's a 1 electron volt. And in my case, I mean, calculated one at 300 degrees of 300 Kelvin is around started. Lowest band is 1.5 electron volts. And this conclusion is actually all conclusions from this one, from this all of this data. We saw that is a symmetric band structure is important because we know the symmetric band structure can be positive things which can further to increasing the, to controlling the relaxation pathway and that one. And bridge chlorine atom is contributing the in contributing in the very deep homo level, one level. So maybe lead halide, although they have a lead halide bridging, maybe we are, still it could be possible to get the feature which is similar to the lead selenide quantum dots, because either chlorine is contributing in the very, it doesn't contribute in the close to the band gap. Another thing is the hole and relaxation rate. Is in case of symmetric relaxation, the relaxation rate is very comparable. But when asymmetric raises, is very interesting that is creating a very hot hole, but its relaxation is very fast. Is giving us to the relaxing to the highest unoccupied state, even almost immediately. And that's all conclusions, and then acknowledgements. Thank you.
Okay, thank you. Any questions are welcome. I do have some. So in your introduction, you mentioned that it's not quite clear why this class of systems is interesting. You tell that 1-7 picosecond excited state relaxation. Is it good or bad?
It's good for solar cell applications because the relaxation time is too longer, so we can separate. We will have enough time to separate electron and hole.
So your target observable is relaxation rate or relaxation time, and you want to make relaxation slower. You want to find material with a slow relaxation, right?
Yeah.
And if you look on your right top, then your hole relaxes over 1.5 electron volts within 200 femtoseconds.
Yeah.
It differs from this declared from 1 to 7 picosecond excited state lifetime.
It is showing that too fast in this
Yes,
case?
yes.
Yeah.
Why it? So
If
first,
maybe-
why it is so
Well,
fast?
I
Here,
would say-
here. No, from-
Asymmetric one is a whole one.
So, is it considered as a good or bad result?
But your electron's not finished yet, right? You're just looking on a hole.
But hole is so quick. Is it good? Is it normal?
It's maybe good in one sense because maybe it could initiate like reverse osmosis maybe or something, that kind of process.
But your methodology doesn't include Coulombic matrix element,
No.
so you are not showing any of those multiple elements. And if you, not you, but community is looking for material with multiple exciton generation, which is quick process. So if your relaxation is too quick, it will compete with multiple exciton generation and will forbid it. So in order to have MEG, you need to have long relaxation.
Well, you assume that your formation of the biexciton taking really 100 like should happen, like really happens in a femtosecond. Your relaxation goes into this.
Okay, so you
Well,
assume
it's a very quick, like this jump, right? For the it's really kind of strange behavior, especially taking into account that you don't have any special. Well, again, it's it's hard to correlate it with really structure of your dose, where exactly this excitation happens, and we talked about it, right? Where exactly you started, like looking on your dose when you're saying this hot hole. where you're taking this hot hole from. Can you show it from your DOS? Like what, at which peaks?
From, yeah, I mean for this one, for this one.
For the asymmetric, am I right? Asymmetric case, it includes hot holes only.
Yeah.
Because the electron definitely is not hot, based on your initial state, right? So then where exactly this energy, like where you are exciting it, either on absorption spectra or from your DOS?
I think those information in the
Where exactly, where's the band where you're taking this, where you're exciting this hole? Because you have kind of this distinct peak, like if you look again on your DOS, right, look, for the holes, right, so you have some distinct peak for either lead or selenium contribution, right?
In these cases, I include, it's excited to the almost 3-band gap. 3-band gap is included like around 3.5 electron volt, and so in this case it's like it's around here in the high intensity video. But I look on that one, but I didn't include it here, and I didn't look on carefully that one. Is it included only in lead or chlorine, or is there any contribution from chlorine? Because chlorine also has a significant contribution here.
Yeah, this is interesting, right?
But the intensity of this peak of the chlorine is lower than compared to this one.
Of course you have, don't forget, you have much less chlorines in the structure, right? Comparing to number of lead and number of seleniums, right?
Yeah.
That's why the intensity of this peak is dealing with just, like, if you normalize your dose by the number of atoms, for example, then they probably will be comparable, because you have how many? 1, 2, 3, I don't know, 8, 24 chlorines versus 600, what it is, 68.
Lead is 80 and
Yeah.
cadmium is 60.
So of course, this is not a surprise that they are much smaller, right? But because you see such a big difference in your relaxation rates of symmetric excitation at low energies, right, where probably chlorine is not really involved, versus hot hole where really your chlorines contribute, and like the overall trend is very different. So there you have more like step-by-step jumps. Here you really have over several steps. It goes from -7 energy to -5, right? In a really very short time, and then it's almost staying in the same HOMA or whatever. So this kind of really probably the thing which might be having some physical reason, or maybe just an artifact or a bug or something, right? But this is interesting behavior, which probably you definitely need to figure out like people might ask, like, why, what exactly, like if it's chlorines, then what exactly they do? Why they really promote such a jump to this HOMA state, or HOMA band, let's say, so quickly, right? Maybe again, projected charge densities for the specific states to see maybe they're really very delocalized or something, right?
In case of, I took the orbital at the 0 Kelvin and also 300 Kelvin in overall orbital. But I saw that in the higher energy orbital almost is delocalized in its whole, but in the lower temperature it's just localized on the middle or vertically. But at high temperature almost all orbitals are delocalized over whole unit cell.
Yeah, then maybe orbitals would be
maybe
more
also,
useful, right? Because this is interesting question, why there's, like, you really see a big difference, right, in behavior, so why is it? And also we have discussed it, like, you really kind of artificially making this this condition, say, symmetric and asymmetric. I would change the title, excitation of the hot hole, right? You can put hot hole versus, I don't know.
Yeah, I already calculated the different one, but
my question is, again, how much really contribution of symmetric versus asymmetric transitions you really have in the absorption spectra, right? So it means you really need probably to compare your overall absorption spectra where all contributions are, and then just the part where you have these asymmetric transitions, right? Average of one sample, 300 or how many ensemble you have. And then the spectra where you have symmetric one only contributing. But am I right that the total energy, like either symmetric or asymmetric, the energy of excitation is exactly the same or close to each other?
I mean, yeah,
Energy of
that's what you mean,
excitation, energy
yeah.
of electron minus energy of hole. In both cases are the same. Like you said, like you excited at 3 gaps or something, but both are at 3 gaps. In one case, you just have luma be like your electron
In
close to luma and hole is deep, right? In the other case, you have both of them little bit to the valence band, little bit to the conduction band. But the total excitation energy is nearly the same for both cases.
Yeah, nearly is the same in both cases. Yeah, the other one is that's a condition for asymmetric and symmetric. That's why in these both cases I put the condition at the 3 band gap, and also in that's why it's always same in the both these two calculations.
Okay. Then this information might be very useful to see how much really realistic your conditions, because your total spectrum, which include like in general, in reality, you cannot say, oh, I want symmetric excitation, I want asymmetric.
Oh yeah,
Because really exciting a 3 band gap, for example, right? And whatever the excitation is there, who knows? You can say, just based on your total spectra, right, to see which contribution would be the major. Or maybe they will contribute equally, means both of them are present, right? And then you really have the then you probably need to consider your total excitation dynamics rather than symmetric versus asymmetric. So in addition to what you want to add, this kind of analysis of absorption spectra, and maybe clearly identify the energy range, like if you say 3 band gap, why not to put it somewhere? And I would suggest to take out the text in the methodology, and probably you'd use the text in your introduction, because again, no one is really...
Yeah, I have to do that because
Go with just main information, which functions and so on. You don't need, again, you can use illustration for showing the, like you have already illustration of your system right on the top, so you can add this information, how big it is and so on, just on this top panel in the middle column, right, for the size of the computational cell.
How quick is the dephasing?
Dephasing is pretty quick. I just calculated this one is same the dephasing when I 3 band gap one is less than 10 femtosecond.
But this is dephasing homoluma between which levels?
Oh no, I mean 3 band gap is still like
initial excitation 3 band gap, and you go to
from the low. Yeah.
Would this dephasing slow down the relaxation?
No. Because dephasing
in absence of dephasing, the relaxation is predicted to be too quick in the surface coping method, because off-diagonal elements of density matrix are assumed constant. But if you include the dephasing, then the relaxation becomes slower. Would this, maybe there is no time to recalculate something, but would this effect hypothetically correct your results towards a longer
This goes to our discussion on Friday, right? Yeah. So, like, what is the actual time for the jump, the correlated jump of the electron versus this dephasing time? But this is, again, we're talking about different things. We need them to look on the dephasing not between excited and final state, but dephasing between each nearest states, right? Because this dephasing information will not really correlate with I think it's not exactly correlating with the issue which you're pointing on. Good?
More questions to Jabat? If no, then thank you once again. Please join me in submitting the feedback to the author.
Thank you.
And we do have 2 speakers more in the remaining 15 minutes.
Again, system size information.
Thank you.
F11.
Who's next?
Originally the plan was for Alyssa.
She's came in empty.
And she's not here.
She is, right?
She walked out first.
Huh? Yeah,
It
but
works.
she's currently here, but just not exactly here.
And there is,
And Braden?
yes. Oh no, let's let Alyssa first because she will finish in time for sure.
What?
Oh,
I have nothing.
you are invited to present your poster.
Well, it's
Come here, do not hesitate.
Oh, okay, all right.
So I nominate this poster as the best poster of the day
Well, I know.
because it has two most important parts: title and acknowledgement.
Right? I got something.
But you can share your plans of how you want to populate the space. And the third way why your poster is the best because you are so generous in allowing your colleagues to provide
Oh, yeah.
comments.
Yeah, it's visually pleasing. So,
Acknowledgement, this is the right one.
not right. But I know.
Okay, let's go ahead.
Why acknowledgement not visible over there?
Oh,
if I
You
do
don't need to write it because you have this
You can
this
move
thing,
it.
right?
Oh,
You
yeah.
take it
I
out.
have one.
Right?
Okay, now it's
So it's the same grant in your case as well.
This is just I'm not sure if this is 100% correct, but I figured I'd at least put something on there.
It's good.
Okay, basically my research involved the difference between a polar and a non-polar solvent on abstracting a proton from thiol and making it into thiolate. And then the transformation between thiol to thiolate decreases the absorption and the light emission. So I was thinking that most of it was
Before you go there, do you have maybe you have your old poster right from November?
Yeah, I have that. I can get that.
Yeah, because at least we will see
Yeah, for sure.
what exactly is the system and what exactly you are talking about. Because
Yeah.
right now, looking
Email
just
it
on
to
empty
Dimitri
spots.
and then he can will open there.
Oh, okay.
Yeah.
2 seconds. If Braden wants to go, then
Oh,
I'm
you have
not.
any pen drive? Oh,
What?
you can connect it directly there and there.
Oh, okay. It doesn't matter to me. Where's the computer?
In a, in the monitor, there have a one USB. Left side of the monitor.
Found it somehow. Okay, good. So we do have a poster.
Yeah, I have
It
an
just
old
has to be
poster.
modified, right?
Yeah. Okay. How do I make this full screen?
Ask Aaron.
Where-
Stuff like that. Yeah.
Well,
And then you
Yeah,
just
you can
move
scroll
it
down
along.
first. Talk
Yeah,
about
scroll
this
it.
video.
okay. So, I mean, right now it'd be great to get ideas of what I should put on the poster. So, actually, I want to go up first. Sorry. So I don't really know what is important in the research that I've been doing. Not that that sounds super bad, but I don't know if I should do information. So my structure is a quantum dot that is cadmium and sulfide, and it's 33 of each, so 66 for the main quantum dot, and that's here. You can see that here. And then I have information on a fully passivated with thiol and fully passivated with thiolate. And then I have like one on each layer, and then I have a couple where there's like multiple on different places, and I don't know what to really put on there. I know that sounds super vague,
But
but
maybe if you put it like not just the structures which you have, but what exactly is the question you want to address? Why you actually making the structures, right? So
Yeah.
what exactly is the questions you want to address, and then using the results from these structures, using the results from that structures, using the results from that structures. Maybe then it helps you better to figure out what is really important and where to focus.
well, the main thing on why we're trying it in acetonitrile, because this is all of my research on propylamine, which is a nonpolar solvent. We're trying to see if the proton is still abstracted from the thiol with a polar solvent. And I'm not really sure that it's necessary to include the data with the means around it, because it's like the means. From the research that I've been doing, I have to go through and sort everything out because I just started this like a couple days ago. Not the research, but the poster. So I'm not sure 100%, but I'm not sure that it's necessary to put the amines in there because the amines are going to have the same effect in both propylamine and acetonitrile. That's what I've seen so far. But my main question is, should
but again,
I
think about it. In real systems, right? So you really expecting that you will have a bare dot with 1-2 ligands?
No, yeah.
You will have really the whole surface passivated, right?
Yeah.
And adding amines helps us to really create the structure, the surface, more realistic rather than just a model, right? But still eliminate the effect of just a single, let's say, what we have, sial or sialate, right?
Yeah.
So like, in other words, because if you have a bare dot with a single molecule on it, the effect might be very different because the other surface is very reactive and doing whatever it's doing.
Yeah.
But if you passivate the other facets with kind of, neutral ligand and then just focus on a single molecule and see how sialate different from sialate, right?
Yeah.
So your model is much more realistic in this case. So that's the answer to your question, whether you need, or you will probably decide whether you need or not, but this is my kind of, answer to your why we're actually doing it. Because yeah, you can just focus on a bare dot with a single molecule, and then when it's completely 100% passivated, like all surface passivated, with exactly the same molecule, right?
Yeah.
But the problem is that having just a single molecule without amines
It's unrealistic.
probably introduce, like your model becomes less realistic compared to experiment, right? So that's why your amines probably really, and some of your results clearly showing it, right?
Should I do like a comparison between like the? I'm just trying. I don't want too many pictures on there, and so
You don't need to show all the structures.
Yeah.
Right?
Just
You
like
can
one
say,
layer.
well,
Should I
here we
choose
have,
a layer?
like for example, on your structures here, you say like we have 21 or how many 20, like we have all surface passivated with sials. Well, we're also working with kind of all of them except one amines. Kind of to, but still focus, like this helps us to really get the idea how a single molecule on a different position will affect the electronic properties, right?
Yeah.
Not the complex, because when you have many of them, they do interact with the surface, they do interact with each other, depending on the facets they interact differently, right? So you have much more complicated processes there, rather than having just one species and then surrounding the other surface with kind of, I would call them fake amines.
Yeah.
Just to passivate the surface to make it less reactive and more realistic.
Okay. So should I do any sort of TDDFT or like the NTOs for ones that aren't, because like fully passivated?
Well, I guess
amines or
except
not?
me, no one probably understands what's going on now.
Yeah, I know.
You probably need to go through it a little bit in a step. So this is your structures. I guess people got it, right? If there are
Yeah,
no
this is
questions.
my main structure right here.
And again, it looks like your goals here to first understand sials versus sialate, to compare the structure of like sial when you have proton and the sialate when you losing the proton.
So right here and here.
Either just
Sial,
losing it,
sialate.
right, and having the charged molecule, or you losing, kind of, it's not really lost completely, just moving to the surface. And then you want to see these effects in a different solvents, in a very polar solvent versus less polar solvent. The effect of the polarity of the solvent, right? So simple.
Yeah.
When you break it into the pieces, then
Yes.
you kind of see.
And then I do have graphs for the binding energy difference. So the binding energy is between the thiol and the quantum dot. It's pretty self-explanatory as far as the labeling. This is without any proton being on the surface, and this is with the proton on the surface. And then this is just the proton.
Here again, you take in a single,
Yes,
how say,
just
charge it.
on
In your
each
case,
layer.
either sialate or sialate with a proton, right? And also in a case when the quantum dot is a pair, and in a case when it's
was
kind of more realistic one covered by
passivated, yeah.
amines, so they're not really introducing really interaction with your between the sialates and so on.
Yep, and then the solid lines here are the ones with fully passivated with amine, and then the dotted lines are the ones without amine. And you can see the difference in energies between. So for
And again, you place this molecule in the different facets, right?
yes.
So you want to see how much this, like which of these facets would be the most reactive, either in this case for sials or for silate, in the presence of amine, without amine. So what is your conclusion?
My conclusion was that the acetonitrile did not obstruct the proton as much as the nonpolar solvent did, and just because I have actual data and I just need to sort my thoughts out. But basically, overall, the polar solvent was better for the photoluminescence of the whole quantum dot.
No, just on this figure.
On
Not
this
overall
one?
conclusions, yeah. Like here you just check in which of the facets are the most reactive, right? Are the strongly reacting with either sial or with silate, or with silate with a proton. So
Not really sure what you're asking. As
We
far as
just-
just with this,
which showing the strongest interaction?
the strongest interaction would be layer B, for most of them, at least for these three. And then the weakest interaction would be C, unless D in this
And if you
category.
compare sials versus silate, which of them interact strongly?
The thiolate with the proton on surface has like the most strong bond to the quantum dot, and the thiol is not very, does not have a strong bond at all.
So the most weakly interacting is the sial.
Is a thiol, yeah.
Okay, so this is a results just based on this figure. And then you probably, if you add the information on a solvent, you can say whether polar solvent changes this trend or not. And I don't remember. Does it change it or not really?
Depends on what it is. It changes the thiolate, the red thiolate a ton, but not much for the thiol here. And then the difference between, I have to look at them now. I can't remember, and I'm getting myself confused. I don't want to say the wrong thing because I know that it's wrong.
This is a new addition,
Yes.
which you will add later, but
Yeah.
kind of presenting it in a comparison in the same way as you present this one.
I
Okay.
feel like most of, I don't know if you guys would agree or not, but this computational, this whole section can be shortened significantly and thrown in my introduction. Sorry.
Well, definitely can be shortened. The only thing you have to understand what you're doing if someone asks.
Yeah, I think I was thinking of just keeping the basis set, and then
Functional, right?
yeah. So probably this first sentence here, because I know that it's 1.5. If somebody asked me, I would know that. I don't know. Do I need this equation?
But do you understand it?
No. I'm working
so
on
what
it.
are each term in this equation? And where you use it for, what is your A here?
For I'm honestly, Levi told me to put it there. I'm working to understand it. I definitely clearly need
But
to.
I think there is some information there for each of the terms, right? Does it?
So what does A stands for? Which of the scientific terms start with letter A? In the two lines before the equation, are there any words that start with letter A?
I mean, acetonitrile, but
And another one?
I don't know what you're asking.
Next
It's
one.
in your
under-
text.
Absorption?
It's in
Yes.
the text.
That
Yes.
one? Okay.
Yes. So do you have data or figures for absorption?
Yes.
Where are they?
Well, they're here and then they're
Okay, so what is absorption?
taking in the energy.
So on the x-axis is
Energy.
transition energy, excitation energy,
Yeah.
right?
And then
And on the y is how good it absorbs at given
yes.
energy. So instead of energy, you can use frequency, omega.
And this is what
Right.
is in this formula, right?
And your equation 1 is A, which is how high the line is
Okay.
as function of incident frequency, omega. So this equation illustrates your absorption
In other
signal.
words, it gives you this complicated shape, red or black shape, which you see on your figure, right? For the
Yeah.
absorption. So this shape is constructed based on this formula.
Yeah.
Again, it's showing strength
Okay.
or intensity at this specific energy, right? And to construct the shape, you need, again, look what you also have. You have sigma there. What is sigma in this formula, like in the denominator?
This is the sum.
No, sigma. before the sum. 1 root square 2 pi sigma square, or whatever it is.
I'm so sorry. I have.
But there is the text, just read it.
Yeah.
It should be there somewhere.
If it is not there, Levi is guilty.
Is it the?
It's not given.
You might have like, look, you have really wide kind of shape. But maybe you can really decrease something to have more pronounced peaks in your curve for the spectral density, for the spectra, right? So actually your sigma is a line width.
Oh.
You can either make it small and then you will have a lot of features there, right?
Okay.
Corresponding to your black and red vertical peaks, right? Or you can make it large and then it would be just big, shapeless curve. So it gives you the line width for your spectra. It's just a parameter which you choose, but actually you can choose it with some guess based on the experimental data, because this is your line width of experimental spectra which are measured, can be measured, right, from the measurements. So then next one, after the sum you have this F, and I think it should be there also. So F stays for the oscillator strength,
Okay.
right? So this gives you the, again, intensity, how strongly it really reacts on this energy of absorbed light at this specific energy. So actually this is your vertical lines. The
This
height,
bar lines.
the height of your vertical lines, right, corresponds to this F, which you get from your calculations. What else it has? And then there is some indexes there, right? So what these indexes mean?
I mean, man, I thought that.
Well, look on your figure and figure it out, right? So your F is just these peaks. How many of these vertical peaks you have in your spectrum?
125.
And they
in this
go
picture,
1,
but
2, 3, 4, right?
For.
Like, look. Like, I don't know, these black vertical lines. They
Okay.
start at some energy, right?
Yeah.
And this would be your probably state number 1, the lowest one,
Yeah.
at this specific energy with this specific oscillator strength.
Uh-huh.
Then you go to the next one, number 2, with another energy, with another oscillator strength.
Okay, so is it the difference between?
No, it's just index of each transition,
Okay.
right? At each energy you have a specific transition.
So omega sub n is frequency of excitation
Of this specific
on
transition,
your
right?
x-axis, and f sub n is height, intensity of this excitation.
So and then you sum over all transitions to give a sharp, or whatever, not sharp, some curve, right? Going from this energy to that energy. If you increase number of transitions, you will have kind of larger spectral range. If you decrease, you will see only the features in front of your, like, you know, the very lowest energy features there.
Okay.
Okay, think about it. And you probably, if you want to use this information, right, you probably need to really know each symbol.
Okay. Well, I'll definitely do that because clearly I did not know that.
Now you do.
Now it makes more sense, right?
Yeah, yeah. And then.
Because again, the difference is if you just calculate your oscillator strengths, right, your spectra will look like just these sharp lines.
Mhm.
But this is not what they measure in experiment. In experiment, they have this line widths, right?
Yeah.
Due to the kind of vibrational motion and something like
Yeah, I feel like that's what I understood. I didn't know the any sort of specifics about it, which obviously I need to work on. It's just the temperature, like this, the Gaussian curve, was just the temperature difference in experimental. You know,
Well,
you
again,
can't do
your
that.
shape
Yeah.
of this Gaussian curve
Yeah.
represents this temperature, because your temperature dictate how much oscillations, how much vibrations kind of smooth out your sharp peaks, right? Because at 0 Kelvin you will have very narrow widths for, well, really almost delta function, like really very, like peaks, right? But if you start increasing the temperature, vibrational motion will kind of smooth it out. Okay, good. So this is technical issues, but
Yeah.
you definitely probably need to reduce it. And again, if you don't want to go to the details for how you're really calculating it, you can skip it out.
Yeah.
But hopefully, if someone asks now, even without this formula, you will
I
be
should-
able to answer at least something.
I know the binding energy. I can get the binding energy. And then I'm pretty sure I have a general idea, and obviously next week I'll have it a lot more
Mhm.
prepared. But it's just like
Any other interesting results
Um,
which you think might be interesting or important, or I don't know,
the
like if you have a density
contribution
of states.
and the projected density of states of the ligand, I feel like is important. Sorry.
Yeah.
Because this is only for the fully passivated, but I feel like it should be. I should include something about having like a ligand only on one portion of it.
Yeah, but maybe not all of them because then
No,
you will
no,
have
because that would
how
be
many?
way too many. That would be
Too
like
many curves,
that
but
would be
maybe
like 30
additional figure if you
more.
want just to characterize specific.
Yeah, but there's specifically a couple of those that I want to put on there, and then
No. But again, if you what's really important about this density of states? Anything to like what is the meaning of these figures?
just pretty much to show where the photoluminescence is coming from, as far as like
This is really ground state electronic structure, right?
Yeah.
So these levels, which of course might contribute to emission spectra, but it's kind of before. It's just telling you the localization of your orbitals on each of the species, chemical species of your system, right?
Mm-hmm.
And then these different colors, again, you can read your legend, will tell. But what's the difference, like what is really important in your top and bottom?
the contribution of the thiol network versus thiol, and then the same thing here, except for thiolate.
So what is exactly this contribution? Just compare the figures, top and bottom, right? So you have some features appearing in the bottom which do not present in the top, right?
The thiolate is clearly a lot more, contributes a lot more towards the end of the, towards the homolumo gap than the...
Of the quantum dot, right? So
Yeah.
you have in states which are completely localized on thiolate, right?
Mm-hmm.
Groups, kind of your trap states, very localized states on a molecule. While the top panel showing that these states kind of not really contribute when you have thials, when they are protonated.
Yeah, exactly.
And of course, this presence of this peak localized on the thiolate trap states, because they have very localized character, and then they will probably affecting your absorption and emission spectra as well, contributing to your absorption and emission near the band gap, like in the lowest energy curve. And this is what you probably see in absorption, right?
Yeah, same thing. Right there and there.
By the way, if it's specified by thiolate, how is thiol coming from?
Hmm?
Is it fully specified by thiolate? I mean, where's the thiol coming from?
Two
thiol-
structures. She's considering two structures. One is completely thials, means you're not protonating it, deprotonate. Like you have proton on the thiol group.
Okay.
And the other one, she's taking this proton and putting it on the surface.
And
on
so
the
this,
sulfur.
I believe, is it going back. Levi helped me set it up, and so I'd have to look at it again. But I believe this is going back towards the ligand itself to make a thiol network, because it's not completely thiol; it's close to it. But
No,
not
she's trying to
exactly.
say, originally she starts with the structure 100% thiol versus 100% thiolate.
Yeah.
Okay.
But thiolate with a neutral charge, because the proton, is balancing the negative charge on the thiolate, and proton is attached to the sulfur on a quantum dot. But then she's optimizing it, and after optimization, some protons from the surface returns back to the molecule, making kind of a mixture between thiolate and thials. And in the case when she starts with 100% thials, some protons disattaching and attaching to the surface by themselves.
Oh, okay.
So due to the optimization, instead of having just thials and just thiolates, she's having the mixture in both cases. But this mixture is not equally just like it's not 50-50%. If she starts with thials, then it's probably stays more like thials, right? If you start with thiolate, it stays more with thiolate or something. But in both cases, you will see some contribution of both species.
So yeah, I have a lot to work on. But and then I'm not sure that I'm gonna put these figures. I don't feel like they add too much, except for maybe just a tiny bit. You can't maybe one or two of these, but you can't really see the difference except for between.
But what does
the
it show,
thiol and
this figure?
thiolate.
What does it show?
The negative or positive aspects of the quantum dot.
Negative and positive aspects.
You mean milk and church?
Charges.
Yeah, that's
Actually,
what I
it's
meant.
natural
Sure,
quantum.
It's the same.
No, well, positive and negative, like, we can consider positive and negative aspects of your presentation.
Most
And
negative.
when you say that it's positive and negative aspect of the quantum dot, it's like saying benefits and, pro and cons.
Okay, I meant negative and positive as far as
Charge,
Yes.
right? So you're showing charge distribution. And this clearly showing that, if you put in hydrogen on the surface, it's not hydrogen, it's a proton, right? So it's really showing positive charge on a proton, more negatively contribution for the sulfur groups, right? Sulfur atoms, sulfur ions. And the Sil group is also having more negative charge if it's deprotonated. So this figure just confirming that, it's really proton, not a hydrogen.
Yeah.
And it's really Sil8 with a negative charge on the surface rather than neutral molecule. And again, maybe it's not important, so this is just a detail which you probably can skip if you have
When
other
it's
results.
fully passivated, when it's fully passivated, it's create almost 3 layers. Like neutral in the middle is more positive negative, and the top is more neutral.
I don't know, she's having fully passivated, right? There are some.
Yeah, fully passivated. In the middle layer is bright green and red, but in the top and bottom is more blackish there.
Because they are. Like, you asking her or you asking me?
No,
What
I'm
is
just
it?
wondering. I mean, how
What is the question?
I rephrase his question.
It's not.
He's
question
asking
actually,
why,
but
if you look on the
okay.
fully passivated case, why your central part is kind of more green?
It's more green and blue, red. Yeah.
Like you have
Separated it for the charge.
distribution between
Yes.
green and red, while the top, like the surface, right, looks more like almost neutral, almost black or grayish kind of.
I mean, my chemistry is not fantastic, but I'm just assuming that these are interacting more with each other because they're not. Distract is not the right word.
But it's not.
but-
It's not a whole surface. It's like top and bottom. Not the. If you look at the surrounding, it's like.
I'm not sure. Well,
That's what I'm just
it
wondering.
just probably is an artifact of the view
Okay,
how it
yeah.
looks like, because if she rearrange it, like showing different facets on the top and bottom, you probably will see pretty much the same. So I think it's really surface effect. So again, why is it more grayish or blackish on the surface?
I mean, I can only guess for like, are you talking about for which one? The top one or for the middle ones?
Any one.
Full passivation.
Full passivation? I want to say something, but I feel like it's not right. It's just chemical intuition, but I feel like that.
What is your? But whatever you answer, don't start with with excuses.
Oh,
So
well,
what is your bar on the right lower part of this figure? Yes. So
This?
what gray color means on this bar?
neutral?
Okay.
So like the surface is more neutral in this case.
Yeah.
Right? Why?
I'm assuming just because the ligands are neutral. Are you talking about the surface for like the surface of the quantum dot?
there is a charge balancing between your redistribution of charges on a ligand, compensating for the positive and negative charge on the cadmiums or sulfur on a quantum dot, right? But the central part has this green and red because it's ionic bond. So you
Yeah.
have to have positive and negative ions. So the nature of the bond is different on the surface between cad and sulfur and the ligand comparing to the bond character inside the quantum dot where you have clear green and red.
Oh, okay. I didn't understand what the question was. I could have gotten that, but
And there might be also a difference between different facets because these facets might be the most reactive, for example, right? That's why they are more kind of like taking more charge from negative part of the molecule, making it kind of less negative, right? And becoming less positive on the cadmium. The other facets probably interact weaker, and that's why this rearrangement of charge is not as strong. So I don't know, it's hard for me to say. You need really to rotate and look. Is it really the effect of the view, or you're really right, it's really top and bottom, and the other face is not really showing this kind of more neutral character. Interesting observation, yeah.
but it still is molecule conserved. It's like,
I think it's NBOs, natural. Okay, so done?
I think so.
Let's thank you. And last but not least, we have one more presentation for today.
Okay, I can't get out of this.
Can you finish in 15 minutes?
I can finish in 5.
Oh wow, great. Okay. And then 5 minutes for questions, right? So we're done in 10 minutes.
So those who will present next time do have a little less time, because today there were 5, next time there will be 7.
Next week, you mean?
Yes,
Next
next week.
Tuesday. But there will be other people presenting, right? 7 new presentations, not
Yes.
the same one which we
And
showed
then we'll probably start over.
in a week,
Yes.
in 2 weeks.
Alright, so I just made this when I came in here today for about 15 minutes. That's why it will be very brief.
So you can do a poster per day. Or a poster per hour.
Anyway, so my project is focused on carbon nanotubes and covalent functionalization of those carbon nanotubes by 2 defects. I claim one is of varying structure and one is always of hydrogen to just balance the valency of attaching one and breaking that double bond formation. So as you can see, it does not look correct in a lot of these places. So here I'm just going to find a way to visualize the different geometrical groups that I'm attaching. I have yet to use my artistic skills to do so. And then here I'm going to kind of discuss, you can functionalize across different vectors with respect to the chiral angle or the chiral axis. And we denote those as a plus angle, a plus plus angle, as you can kind of faintly see here, and then a minus angle, and those are just vectors. And you can take those to be ortho or para, crossing the ring or adjacent to the ring. So if you take a look at this top one, I have kind of a rough binding energy graph here with a bunch of different groups. So as you can see, I've normalized, so I've taken it as a relative to the same group. So I found the
Your
lowest.
call will be disconnected.
I found the lowest binding energy, or the lowest total energy of the system, and I subtracted it by all the other groups. So one of them will be at 0, and the other ones will be relative to that.
Keep talking. And it is a reason to print posters in case of such situation.
Sure.
Means send it to Dmitry ahead.
It's not actually a question, it's just one clarifying. Is you said that create a functional, you're doing functionalization by creating defect. Is you are doing defect or functionalization? I guess there is some difference.
Well,
Okay.
Now just only we can see that.
You are creating any defect
but
or
the
you're
guy
well,
doing
is
so
functionalization?
it's a
Yeah.
functionalization is
But
probably
not a defect.
more proper because it doesn't interfere with the tube itself. It's just a covalent attachment outside of the
Yeah.
tube.
You probably need to explain what exactly means the defect.
Yeah.
Like in what context you talk, what kind of defect you are talking about.
Yeah, that's why I'm kind of hoping I'll get this. I can show the tube, and then I can show the defect atoms on top of the tube.
Well, this looks more like functionalization rather than defect.
Is it
Yeah.
functionalization
Yeah.
or defect?
What is a defect? What kind of defect it introduces?
Okay, I guess he didn't get it. Is it defect or is it functionalization?
It's a functionalization which results in a defect. The
Oh.
question is, what is a defect?
The defect is a broader category, I'm assuming.
Come on, what kind of defect you create? What is a defect? Like, what is a defect?
What do you ask?
You start with a
Shortcuts.
nice unit cell for the nanotube, pristine nanotube.
Yeah.
Now you put a functional group.
Yeah.
Then what it does with a unit cell for the tube?
If you have carbon atoms on the pristine nanotube,
Yes.
which hybridization do their electronic orbitals experience with neighboring?
Well, sp2 in the pristine, and then
And now when you introduce a functional group, your
shifts to a more SP3-like hybrid.
goes to SP3. So it's changing the bond character.
okay,
This is
got
your
it.
defect, right?
Okay,
So you're kind of really thinking that now instead of resonance structure, honeycomb,
Honeycomb.
yeah, you have in really one specific cell where you have single bonds rather than single double.
Okay.
So it's you can say it's either SP3 defect, right, introduced, or you can say defect in a conjugated structure of the nanotube. So you put the functional group, but in a such way that now you're changing the geometry of this single ring, right? You don't change the whole geometry of the entire tube. You're just changing local, and this is your defect now. From the geometrical point of view, it's a defect.
Yeah.
Nice.
So
We're now watching you.
Really?
Is it you playing? Oh, you have 1, 2, 3.
If you wave a hand, it will be most impressive.
You have 5 rating.
Okay, cleared up? Okay, so yeah, like I said, just looking for the binding energy to see if any site has any particular tendency to hold on to these defect groups more than another. Another interesting thing, I obviously don't have as many groups on this plot as I do on that, I'll update that, is the band gap. So obviously per defect group, the band gap changes very negligibly, but across different geometrical orientations across the ring, ortho, para, and along the vectors, we have a pretty nice change in the band gap value. I don't have plotted, of course, the pristine is somewhere up here, but
Yeah, that's why we probably need to show the difference, right? Between the band gap of the functionalized tube or defective tube versus the pristine tube. So then it's easy. The smallest difference would be clear.
So then, of course, I have a lot of absorption data for each of these configurations and for each of these groups. And from that, I've chosen the first bright state, so in the pristine tube, it's the third. The third state is the E11 transition, and then in the two most blue shifted, or not blue shifted, but slightly red shifted configurations, the third state is still the first bright state, but in all the other configurations, the first state is the first bright state. And I, of course, have natural transition orbital plots for all of those. So I need to figure out how I'm going to reduce all that. Dr. Klein and I talked about using cube files and trying to get a quantitative measurement for all of the sizes of these excitons. To try to get that on a plot, greatly reduce the space needed. And also taking the difference between the E11 and then all the E11 stars, and putting that on a plot would also greatly reduce the space needed and show all of the data that I have. Because this plot is the absorption for all the configurations with the pristine on top of one defect group. And as it happens, as you can probably see here, changing the group itself doesn't change binding or the band gap a lot, and it won't change the absorption plots hardly at all. So that's why putting it on one plot is going to be a lot nicer. It won't be too chaotic. So that's the brief rundown.
So can you give a little bit more insights into your binding energy? How did you calculate it again? You just subtract the energy, like this is not binding energy, it's total energy, right?
It's, yeah, the subtractions of total energies within the defect group. So,
but what exactly you subtract?
so I have the total energy of
Each
this,
system, right?
of each system with the same atoms, and then I subtracted. So I started with this one, and I subtract all of the other configurations to just get a relative energy from that. Does that make sense at all?
Like you have all configurations with the same number of, with the same molecule, right?
Yep.
And I've still lost the main part. And then you subtract the total energy of each of this configuration from
from one of them, and I choose that one
Oh.
of them to be the lowest one.
And this lowest one,
Oh, so
but
that's
on
the
your plot,
relative
am
energy.
I right? On all your plots, looks like your except two lines, right?
Yeah.
For all other lines except the two ones, your lowest configuration corresponds to this. I think it's O plus or whatever your notation is there. Right?
Yeah.
So they all coincide with this O2 plus, except these two guys where it's backward.
Yeah, and I'm not
It's the largest for O
100%
plus.
sure why that trend is backwards. And there's two lines. There's actually only one thing because I'm calculating all these with the STO 3G basis set, but just as a test, calculated with 631, and they show the same trends when they're scaled. So it's just a confirmation. But I still don't know why it has a backward trend. I maybe screwed up something, so I'll have to go back and look at the numbers, make sure my calculations are correct.
But again, since if we believe to your difference in energy, right, with respect to the lowest configuration for each case, you can't really differentiate. You can't really say which of them really is the most pronounced, right? Because the difference is so small. So they're kind of in a KT range. So it looks like all defects, all positions really can present at the same time. And the only difference would be, but this is actually interesting, if we believe, if it's not really an arrow, right, then the molecule with the longest molecule with fluorines, right, which have completely reversed trend, telling you what, that now you have the, well again, the difference not so big, but looks like you still have a little bit more pronounced, like little bit more tendency to have O plus structure, kind of should happen more frequently, comparing to the O backward. Actually, O plus should happen less frequent, right? Because energy is higher there than for other molecules, right?
Sure.
And then it means that just looking on this O plus, where it's more thread shifted or less thread shifted, then it looks like you will have probably spectra with with the opposite sides for short case when you have, let's say, CH3 comparing to, or CH3 F3 comparing to C6 F13, right? So might be, again, if the value, the difference is really very little here. Also maybe not. What's the difference then if I look on the scale? So it's like still less than KT or in a KT order?
It's less than KT. But in order
It's almost 100th time of KT. No, 10th time of KT.
What is KT? 0.25?
Yeah,
0.25.
0.025, yeah.
And honestly, that might also be a convergent thing too. So I made this plot very quickly.
So recheck it, but interesting.
Is it atomic unit or electron volt? Are you sure?
Well, the attempt was electron volt, but we'll see.
It's like it's insignificant then in this case here. Binding energy. If this in electron volt is in very insignificant energy difference.
No, it's electron volts, right?
Yeah, but it's
Yeah.
0.0002.
Yeah, that's what I said.
The
Like, it's
answer is
really not very different. Like all of
Not
the
that
structures
different,
really
yeah.
present at the same time. But that's why we need to recheck that it's really right units. That it's not just
But
multiplied.
can he correctly calculate the binding energy?
Some estimation.
No, I mean taking the two separate.
It's a good question. Why we taking total energies instead of binding energy? Answer.
Because you don't know the chemical reaction that does that. You can't compute the enthalpies.
Well, you know your functional group.
But it
And
would
you
be
don't-
radical. If you disattach it from a tube, you make it a radical.
Yeah, there's no way to recover that.
Because if you
It's
need
more
you
complicated
need
reaction. You
hydrogen
need
there, right?
to
To have a neutral
add
molecule.
or remove two ligands, or you need to put hydrogen, create double defect, and it gets too complicated.
It's different from these molecules, which, for example, were shown by Erin. No, you didn't show. You didn't. You
The
came
Lisa
probably
was
earlier.
showing.
But yeah, that Alisa, because her molecules really just. It's exactly the same molecule as it was by itself, and when it's attached to the surface.
Both of them are neutral.
The molecule is not changing, but here it's really creating a it's an organic reaction, which really you losing hydrogen from wherever your chain or from the benzene ring, and creating carbon-carbon bond. So it means when you disattach, you get in a radical. and then you really need to know kinetics rather than just thermodynamic curve.
Mhm.
Yeah, so this was really a question. Can we calculate the real binding energy? Looks like not so so easy.
And
So-
that's why I could only compare across different groups of the same.
Yeah,
element
so
too.
for us it's really hard to compare molecule 1 with molecule 2, but we can compare at least the position, like how each position different. And electronically,
This relative, yeah, delta.
right, but electronically the difference is very big, right? Because we have very big redshifts depending on the position, but looks like we don't differentiate, like each of these positions can be present at the same time. So we cannot say that this position is the best one or the most probable one.
So did you use the STU basis set for all of the calculation?
Except,
Except these
Well,
two.
yeah, except the two.
So you will get all exactly opposite trend and by using the 631 G star basis set, right?
No, this curve on the bottom and this curve right here are 631 G star. And so this blue one on top and
Oh, okay.
the other one in here that this one matches to
Oh, okay.
is
Okay.
still,
I
so,
didn't-
yeah, no, it's,
No, that's fine then.
they match up with the factor, so it's fine.
so looks like we don't have really effect of the basis set, but we have one molecule which really having kind of, a little bit different trend, but if they're not really different, if the value is so small, then it's still not very much useful.
I'm hoping I just screwed something.
One comment on your reference. This is not the Gaussian reference. They're very picky on that, yeah.
Any more questions to Braden? More questions 1, more questions 2, more questions 3. Well, thank you once again. So,
Okay, good. So you guys have another week to polish everything, right? And we hope not next week, but next Tuesday, right? Actually 2 weeks, I would say, right,
Okay.
now. So we hoping to really see more or less almost final product.
Yeah.
And then will be really small corrections.
those who are
Yeah, I just had no
web
time
powered
to do this,
was
you know.
prepared
Yeah.
to,
But that's why we're doing it,
present
like, we
next
have the
time.
full month to train it. in
Yes,
advance.
exactly. Perfect.
and you've got the chance to see how it
So
goes.
next week is gonna be all the other people. Thank you.
Which also you might kind of check how